Question 60, you've got f of x here equals 1 minus 2 over 3x squared plus 2. Part A then, it says show that f dash of x is always positive. Now notice there's f dash of x, right? Not f to the minus 1, okay? F dash of x is quite simply the derivative, right? So f dash of x is another way of saying dy dx. So show it's always positive, so we need to do dy dx of this. So if you're going to differentiate this, right, what I would do is, first of all, I would rewrite this as 1 minus 2 and take that up, 3x squared plus 2 to the minus 1, take the bracket up, because you can't differentiate it as it is here. You could treat this as a quotient, but seeing as this is just a constant here, just take it up, and it's easy then to do f dash of x. So f dash of x, differentiate, 1 becomes 0, and if you differentiate this, the minus 1 comes down, so it becomes minus 1 times minus 2 is plus 2. Take away power from that, so you get minus 2. Take away 1 from it, you get minus 2. Times then the derivative in there, which is 6x. So you end up having, on the top, you get 2 times 6x is 12x. And then take that down, so you get that there. Now it did say, show that f dash of x is positive, right? And actually now, straight away, I can say this is positive. Simply because, if you look at the domain, right, and it's good to write this up here, if you look at the domain of f of x, domain is positive, isn't it? Okay, domain is positive. So if the domain is positive, then all the x values are positive, aren't they? All the x values are positive, okay, because the domain is positive. Okay, the domain is the x values, so they're positive. So that means then, if x values are positive, 12x is positive. Okay? And of course on the bottom here, this is going to be positive. I mean, because it's squared, we know it's going to be positive, right? Because it's squared. So, we've got f dash of x is equal to a positive number divided by positive, which it leads to being positive. Okay? So the gradient is always positive, and that is really useful to know that when it comes to functions, because some functions like this, we don't actually know what they look like. Okay, if I was just to draw this, I wouldn't have a clue where to start. Okay, and it could be any sort of curve. But in this case, because they say that, because we've worked out the gradient's always positive, this graph is always increasing. Right, there's no dips, and it doesn't go up and then down, and up and down. Right, it's constantly going upwards. Okay. Constantly going upwards. So it might look something like this. Okay, it might look something like that. It's always going upwards. Forget this bit here. Okay, no, that's a bit dodgy there. I didn't mean to do that. It's always increasing, right? If it's always increasing, that means with the domain value that we've got here going from 0 to infinity, in order then to get the range in part B, because it's asking for the range, we know for the range, the lowest value in the domain will give you the lowest value in the range, and the highest value in the domain will give you the highest value in the range. We know that from the fact that the gradient is always positive, so the graph's always going up. So as I said, the first value in that domain will give you the lowest in the range, the last value in the domain gives you the highest in the range. So that's quite nice then when it comes to the function. Okay, if I write this out again, we can work out the range quite quickly by putting 0 in to give us the lowest value in the range. Okay, so 0 will go to 1, take away 2 over 3 times 0 squared plus 2. So that works out to be 0. Okay, and then infinity, put that in. So you get 1, take away 2 over 3 times infinity squared plus 2. Well, you're dividing by infinity here, so 2 divided by massive just goes to 0. So this will be 1, take away 0, that's what that will go to. So we get 1. So you can see then the range will be a 0, 1, right? And then they won't be included because the domains weren't included. 0, 1. Okay, the lowest value in the range will be 0, the highest will be 1. Okay, then part C then asks for an expression for f to minus 1 of x, right? So here you've got y. So let's rearrange this now so we get this in terms of y, so we have x in terms of y. So what I might do is I might swap these around. So I'll take this over to the other side, like that. So take the y over this side, so it becomes minus y. Take this over this side, so it becomes positive. Then what I might do then is I might swap these two. Okay, so because you divide in here, take it up in times, and then take this down and divide. Okay, then I might take that minus 2 over, that plus 2 over, so it becomes minus 2. Then I might take that 3 over and divide, because you're timesing here, so take it over and divide. So maybe the best way to write this is a third of it, rather than divide the whole thing by 3. Okay, then, of course, to get x, I've got to take the square over and square root. So when I square root, I need to do plus or minus. Okay, then I need to decide whether it's going to be positive or negative. And all you've got to do is go back to the domain. If you remember the domain, go back to the question. The x values are positive, aren't they? The domain is positive. So you say, look, since domain is positive, i.e. x values is positive, take positive root. Okay, so therefore f to the minus 1 of x would equal then the positive root, and put it in terms of x then. Okay, and you're done, you've got your inverse function. It says then to state the domain and range, and remember the domain is simply the range of f, right, which we worked out earlier. Okay, so the domain of f to the minus 1 of x is the range of f, and then the range of f to the minus 1 of x is the domain which is given to us of f. Okay, so we just swap them around, job done.